So today, the first experiment that we're going to talk about it's called I-beam bending. Um, as the name says, it's I-beam, meaning you have the cross section of your beam. It looks like an eye, and since it's bending, we'll apply a bending force in it, and we'll study how the applied load can affect the material and how it can make it undergo deformation. To get into the topics, first you need to know what are the types of stresses up there. So in broad context, we can divide the stresses into two sections: axial and bending. So axial or normal stress usually it's when it can be defined as a specimen's resistance against axially applied load. So if you look at this example, this is your beam, and you're putting force that's perpendicular to its surface, right? Now, if you take a cross section and if you analyze surface by surface, you'll see the nature of the load. It's whatever it is on the top. It's same in center. It's same in bottom. And all of them, the same equation you can apply in all these sections to define stress. Um, so axial load, they can also be divided into two sections: tension and compression. So if something tries to stretch it out, that's tension. When it's compressing, it's compression. Then comes bending. You can see the direction of the load. It's a little different than here. You have forces parallel to your longitudinal axis, where you have forces in here that's perpendicular to your longitudinal axis. And when some specimen goes a deformation like that, its top surface, it's if you look at it, you see that it's stretching, it's in tension. However, its bottom surface, it's in compression. So that's different than axial forces. So if you take the cross section and if you analyze layer by layer, you see on the top, you might see tension. For this case, I mean that's a different specimen, and that's a different load cases where you're forced trying to like bend it like that, like an U curve. So if you take a cross section of this case where you have two support, one force that's pushing downward, you'll see that on the top you have compression. On the bottom you have tension. So your specimen goes from compression to tension, meaning from positive to negative. So there has to be a point where there is no stress at all, and that's your center axis. So there is no stress that doesn't like no stress acts on it. All right. And just as you have resistance against normal forces, you have resistance against bending forces. The more mass you have in a specimen, the tougher it is to change or deform anything axially, right? Because then you have to deform more material if the material is more thick. Similarly, when you're bending, there is a thing called second moment of inertia or area moment of inertia. So that actually tells you the resistance against the bending forces. It's a little different than regular inertia because this inertia also depends on which axis you're using to bend the stuff at. For example, let's say this is you have a beam, it's a rectangular beam, and your cross section is not uniform. So you have two cases. One case is you bend it like that with a cross section that looks like that, and then you flip it and then you bend it with a cross section that looks like that. So if I ask you which one would be more harder, intuitively you can tell that this one is more harder to bend, right? And why is that? Um, it's because it's because if you remember this picture, your top surface sees tension, your bottom surface sees compression, and the topmost surface sees the most tension, and the bottommost surface is the most compression. So, what's the point of having so much material in the middle? Why not I concentrate all my material on the top, because this top surface is going to see the maximum, is a crucial area because it's going to see the maximum stress, and also in the bottom, and just take out material from in the middle. It lightens up, it reduces the weight of my specimen, and that's exactly what happened in I-beam. They take out the material in the middle, they concentrated the material on the surfaces, on the top and on the bottom. So if I compare it with this analogy, I would say this specimen, this cross section is harder to bend because it has more material uh, distributed from the central axis or from the bending axis, right? This specimen have more material uh, far away from the bending axis than this material. So definitely, if I use this, then I'll end up with two different axes, actually three different axes of uh, allegedly bending. And my strong axis would be if I try to bend it like that along along y-axis, and my weak axis would be if I try to bend it like that along along z-axis. All right. So the point is, your area moment of inertia is the resistance against bending, and it depends on which axis you're using of. So these are the equation. When you're trying to find the moment of inertia along x-axis, your b, which is your width in this direction, and your height, q, right? So that's gonna be your equation. But just when you flip it, your width is gonna turn into your height, and your height is gonna turn into your width. So you just flip the parameters. All right, now I will give you guys a few minutes to draw the shear and bending moment diagram. So you should learn it. You should have learned it in your statics or your kinetics classes. So I'll give you 5 minutes. You draw it, and then uh, you share it with us. Hey Diego, if you're done, you can start sharing your screen now. Yeah, I think that looks about right. Cool. Thank you. All right. Is there anybody else want to share? Okay. Well, Dia got it right. So it kind of looks like that. Your shear force diagram. Remember, even though you're seeing 10 Newton applied over here, you actually have 10 Newton over here and two reaction forces on these two ends. So what's going to happen that you see the effect of 10 Newton the most in the middle and the least on the two sides. So that's what kind of gets reflected in the shear force and in the bending moment diagram. You can see as you go far away from the center, the effect it goes smaller and smaller. Eventually, on the support, it becomes zero. All right. Do you guys have any question on that? So that's how your experimental setup is going to look like. You have this is your I-beam. Um, okay, so before that, let me tell you what you are trying to achieve in this experiment. So, um, okay, so you have your I-beam that looks like that. Now, everything that I've told you so far, your experiment is to verify them. Meaning, in your I-beam, you have sensor devices at different points, like on your top surface. This is your top surface. Some sensors in the middle, some in the bottom, right? So all these gauges, it's gonna give you strain value at different points. So what you have to do, you have to calculate the strains at different points theoretically, and then you have to compare them with these values that you get from your computer. All right, so this is your first task. And then second, uh, you find out the moment of inertia, and then you draw the free body diagrams, meaning you draw the shear diagram, you draw the bending moment diagram for this specific case. Now, this is how your beam is going to look like. So you fix your beam on one end, and then you put you put bending force on other end. So that device over here, like you can see this little wheel, you can turn this wheel and you can put force on it. You can control the amount of force on it. So your that end, it's fixed, it's this end. And your this end, your free end is this end. And you're putting force from top to up. So you're putting upward forces. And that force will try to bend it, that force will try to make it deform, the force will put it through strains. And your job is to theoretically study them and then analytically check them with the experimental data to see if they're accurate or not. Um, so we call them 606126 aluminum I-beam with strain gauges A to Z. So meaning you will have uh, 6 strain gauges numbering from A to 6, A to Z. Actually, 7 strain gauges. Yeah, and then you have a load cell. But before going in there, let me tell you what strain gauges are. So strain gauge, it's pretty much a circuit with a fixed uh, coil or fixed wire length. So this is your wire, and the property of it is that if you strain it, the length is going to change, and if the length is going to change, your resistance is going to change. So the electricity that's going to come, like that was coming earlier, you're not going to see the same thing when you put it through strain. So it's going to tell you what strain your specimen is seeing, and it's all the strain gauges are connected to this load cell. So you can just switch the knob, you can change the knob, and it's gonna tell you what strain you're seeing at what gauge. All right, and all the data they're gonna get shown in a computer software that kind of looks like that. So you see that you have A, B, C, D. A is your top one, B is your bottom one, and everything else is in the middle. So it tells you the place of different strain gauges. So yeah, like this is how the um, outlook looks like. How do you carry it out? This is also a schematic of where these strain gauges are. You can see that A is in the top, D somewhere in the top, around the top, G to E they're like in the middle, and then C and then B on the bottom. So how do you do it? First, you position the load cell directly under the central vertical axis of the I-beam. I guess you guys already understood what it means. You just fix it. You fix the I-beam on this machine. You put force at this point. So you need to make sure that everything is fixed. Crank load cell up until it touches the bottom of the beam. So that's a wheel where you're going to turn the wheel and make sure that the load cell is touching the bottom of the beam. And then you crank in 50 pounds of load, because I believe the maximum load this specific beam can take is around 55 or 60. I'm not exactly sure, but this is like maximum we use at the lab, at the experiment. And then we're gonna read and record the strain values at strain gauge, and then get the experimental values for the strains. All these procedures are explained in a couple of videos that I'm gonna share with you. I think I didn't attach the links in here. Oh, actually they're here. Yeah. So you can get in there and see the experiment by yourself. Okay. So with this setup, you can do bending test with a lot of different cross sections. For example, this is where they're using a hollow shaft. So this is going to be one of your experiments as well, how to do the analysis of a hollow shaft bending. This is how the load cell looks like. Just go through all this stuff because I need you to like study this, and in your theory section you condense this knowledge and write down what's important, what's necessary to explain this experiment. Okay. Yeah, so that's the same thing. That just tells you how they cranks it, like how they fixes it, the details. So this is where your piston load cell. It kind of looks like this is where it's gonna give you a reading, right? Okay. All right. So the steps, there are more details explained in here. So make sure that you just not only see the videos, but also you go through these steps, because video is a continuous thing, right? And these steps will tell you what are the principal, what are the most important things of the experiment that you need to keep in mind. Okay, try to answer these questions For example, what is area moment of inertia? Why do you need to know this? Calculate the cross-section modulus of I-beam. Why is it important? Why modulus of elasticity is important? So answer all these questions in your report. So what is modulus of elasticity, or why this is important? These kind of descriptive questions, these descriptive answers can get into your theory and introduction section, and the analysis of the data of the results will get into your report and discussion section. Okay, Diego's asking that if that file is going to be shared. Yeah, the file is going to be shared as well. Okay, so I already told you guys that I want the area moment of inertia. So you do the theoretical calculation, you do the analytical calculation, and compare them. Then you find out the modulus of elasticity. We already talked about modulus of elasticity on the previous class. So go through those materials if you want to remember them. Draw the load, shear, and bending diagram for this. So what you drew in this class, you just draw the same thing, but for this specific case. All right. These are the equations that you might have to use in your experiment, in your report. So everything is right there. All right. So that's how your data, the data that I'm gonna give you, is gonna look like. So it tells you each strain gauge and what are the loads: 0 load, unload, 15 load, that's our maximum case. And then what are the experimental strain that you're getting all these things. All right. Okay, so I think that pretty much explains the theory section and your job of what you need to do in the report. Now I'll pause for a minute or so and ask you guys if you have any questions.
So just to go over, when we do the results and discussion section, I'm assuming that's where we require most of the calculations. So it was take theoretical gauge pressure, different points, moment of inertia with free body diagram, section modulus for the I-beam, area moment of inertia, modulus of elasticity, while drawing the load, shear, and bending diagrams, calculate the normal stresses due to bending, and then as well as all the other equations that you posted on the last couple of slides.
Yeah, so all these other equations that will get into the things that you just described initially, like modulus of elasticity, strain. You'll need these to calculate those. You know.
Okay.
Yeah, and everything else, yes, you're pretty much right. The shear moment diagrams, the theoretical and analytical comparison, and the parameters, yes, they need to be calculated as well. All right. So the second one for today is mass spring system. We'll study the mass spring system. We will see how the spring element reacts when a load is applied to them, and determine the relationship between the applied load and spring stiffness along with information. So the first thing is we will study, like, we'll put a load under a spring, and we will see when the load is static, how it changes the spring, and when the load is oscillating, how it's changing the spring, and what's the relation between the spring stiffness and the applied load. Intuitively, you can say the more the load is in here, the more deflection you will see. So to understand that, the first thing you need to understand is what is stiffness. So stiffness can be described as the spring's resistance against loading, meaning the force you need to make one unit displacement, right? So if you need more force to make one unit displacement, meaning you have more stiffness. If you need less force, like smaller amount of force, then you have smaller stiffness. And the simple harmonic motion, okay, we'll get into that. So what's a simple harmonic motion? Simple harmonic motion, it's when you have this, for example, when your spring, it starts deflecting from point A, goes all the way to the bottom, and then again comes back to point A. So when it completes one complete motion, this is what we call a simple harmonic motion. All right. Give me 1 minute. Let's see. Okay. Yeah, so this is a comparison of how simple harmonic motion between a pendulum and a spring mass system would look like. So in analogy, they both are the same. This one is going from here, reaching up there, and then again coming back here. And this one, it's starting from here, like going all the way to the bottom, and then again coming back here. So that motion with where some specimen comes back to its initial position, we call it simple harmonic motion. And for different kinds of motion, it depends on different kinds of parameter. When you have a pendulum, it depends on the length, meaning the length from this point, the connection point, to the center of the circle. It's directly proportional to that, and it's inversely proportional to the gravity. For what the spring mass system, this directly depends on the mass of the system, and it's inversely proportional to the stiffness of the system. Meaning, if your spring has a higher stiffness, has a higher resistance to external force, then it's gonna come back and forth like faster. It's gonna do it faster. But if it's less stiff, then it's gonna take more time to complete one full motion. So once that concept is clear, let's take a look at the experimental setup. It's pretty straightforward. You have this spring up here, and then there's a slot. On this slot, you can put the weights, and we will have, like, these are the weight plates. Each plate has consistent and similar weight. You can just put on, you can put them up there incrementally, and you can check the effect of different weights for different spring. These springs are modular as well. You can replace these springs. So with these advantages, what we did in this experiment, we studied different load cases. We applied different loads, and we saw how they change the deflection, the length of the spring, and how they change the harmonic motion time, simple harmonic motion time, or T, for each spring. We changed the spring. We started with a spring with less stiffness, and we went up to a higher stiffness spring. However, the stiffness, it's not being mentioned in here. You have to calculate the stiffness based on the deformation and the harmonic motion. Okay. So what do we do for the experiment? What are the procedures? Definitely first set up the whole thing. By the way, this thing, it's not, it might look like that there is a glass cover, but there is not really. I mean, it would be great if we could have covered it and make it like do the experiment in vacuum, but I guess it's just not worth it for this case because the losses would be too minimal. So we first put the helical spring and then we fit the rod and plate into the guide orifice, meaning we need to make sure that the oscillation is happening, it's always constant with with its alignment to the central axis, because you don't wanna move it like or tilt it or do something else. Then your study your results is gonna be get all crooked, not what you're looking for. Measure the dimension of the spring, including the diameter of the wire, and the number of coils, because it's important for you to figure out the mass of the system, and also to do a theoretical calculation on the stiffness. Okay, so first what you do, you put the weighted disc on the platform, and you keep putting them up until you reach 4 kilograms. And for each cases, you study the deflection. And then you take the discs off one by one, and you measure the unloading deflection. And then you get an average stiffness. After that, the second stage will be put a weight disc on the platform, and then push it a little bit, and let it complete oscillation for let it complete 20 oscillation, and see what time you need for that. From there, you can get a simple harmonic motion time period. Okay, for the first part of the experiment, that's your spring 1. You put up the masses, you note the heights, you get the deflection. You do the same thing for spring 2, and you do the same thing for spring 3. So from 0 you go up to 4 kilograms, and from 4 kilograms you again come back to 0 kilograms. So you have a lot of different data sets to calculate your stiffness. See, your K, it depends on your F and X, the force you're applied and the deflection. And then your F is dependent on your mass of the system, of the weighted disc. So you will have a lot of K values. Just compare those K values and find average K for each specific spring. Use that K over here to calculate the time period, the theoretical time period. So now you have your stiffness, you know the mass of the spring, and you know the time period. So from there, you move on to the next step of the experiment. You'll do an oscillation test. So in the procedure we explained that you need to record the time for 20 oscillation. You can do it in another way as well. You can let it oscillate for 10 seconds, and you can point out, you can note how many oscillation it made. So just for an example, when you have 1.6 kilograms on spring 2, it did 30 oscillations for 10 seconds. You divide them up and you get the experimental time period. And then your task is to compare the experimental and theoretical time period. So what I'm expecting from you over here, this is your first graph that needs to be in your report, that will kind of look like that, but it depends on how your values look like. It's not exactly going to look like it. You can see that you have 3 springs with 3 different rate of stiffness, right? This one is more steep, this one is less, and this one is even less. So you can see from this equation that the force is proportional to the deflection, and it needs a constant to make it an equation, and that constant is its stiffness. So figure out which spring is what and why do their curve look like that. That can be a paragraph for your description in the result and description section. Sorry, discussion section. So you can make this table from the from table 1, 2, and 3. The first 3 sets of experimental data, and this one you can make from table 4. So that's another curve, and that explains your tau square, your time period square, with different masses, and the theory compares the theoretical and the analytical values. Now, why do you need tau square? Why do you need time period square? It's simply because your time period accounts for the time in the positive and the negative direction, right? So your deflection, let's see, yeah. So your time, like your specimen, half the time is moving in one direction and half the time is moving in another direction. To normalify that, you need to square it. All right. And what goes in your lab report? On a theory section, you explain all this stuff. On the methodology, a brief description of your procedure. And definitely you write down in your own understanding how you would run the experiment. Remember, there is no wrong answers, just answer to your understanding. And then apparatus, what are the apparatus you're using? And finally, this section. I think I already kind of like gave you guys the idea, but just to sum it up all. Detailed calculation of K, stiffness, and time period. Analysis of the result, like why each spring has its different stiffness, and then comparing the values, and finally the graphs. All right, that's about it. I guess that's pretty simple compared to the first one, but your first experiment, which is I-beam, will be due on next week, and the second one, this one, will be due on the week after. All right. Okay. So question time. Yeah, Diego, go ahead.
So for when you say we need to make our own spring deflection graph as well as the math, excuse me, as well as the mass versus tau squared. We're just making the data that we're drawing to make those graphs from, the data we're getting that from is the data generated by the experiment already, right? We just need to make our own graphs.
You need to make your own graph for your analytical tau, and also you need to put your theoretical tau square. I guess that's not shown in here. So yes, you get the tau values from your experiment and your theory.
Okay.
Anyone else? Okay. All right then. So I'll stop the recording here, and I'll wait for a bit just in case if you guys have any question, any non-technical question, meaning your report or your previous experiments. Yeah, Diego, go ahead.
I did have a question. When should we be expecting a grade for our lab reports?
By next week, yeah.
Okay, thank you.